We're gonna add some decorative items next, the buildings and the trees. And we'll just focus on the bases first. Fancy stuff comes later. Now, with few modifications, we could use the same graph editing tools to generate the bases of the buildings as well. But I think it's really tedious, especially if you plan to build really big worlds and if you want things to align just right. So we'll reuse the functionalities we already have and implement an algorithm to procedurally generate buildings next to the roads, and then just place trees randomly where they fit. This solution does have a downside, that you cannot have a building exactly the way you want it, but I think it really compensates for that because generating everything becomes so fast and easy that you actually could build Rome in one day. Get it? Because Rome has buildings. No.
Gonna code, debug, and have fun. Coding with Radu. Coding with Radu. Gonna prototype and design. Coding with Radu. Coding with Radu. Let's code now.
Let's go to world.js. And here in the constructor, add some more properties for generating buildings. I'm gonna align these a little bit different because there will be quite many things appearing here. First one is the building width. And then the building minimum length. The length will vary depending on the size of the road segment. But I want to have a minimum value, and in this case, setting it the same as the building width means that in the worst case, we will have a square building. Otherwise, it's just going to go alongside the road. And the spacing is so buildings don't get stuck to each other. Now, let's set these values here as attributes of the world. Like so. Building width. The minimum length, and the spacing. And let's store the buildings here in this array. Now we'll generate the buildings inside of the generate function here by typing buildings is equal to this generate buildings. We'll write all the functionality in this private method.
The algorithm will go like this. We first generate some thicker envelopes and use the same process as before to get the outer segments. From these, we keep those long enough to support at least one building. And if they're really long, we divide them into multiple supports like this. We then generate a poly around each of these using envelopes again, and do a little bit of fine-tuning. You'll see.
Generate buildings. Let's first get these thicker envelopes. I'm just going to call them temporary envelopes because we don't need them afterwards. From the graph segments, we take each segment one by one and create an envelope using it and push it to this temporary envelopes. So the envelope that we're going to create has the segment as the skeleton, but then the width we have to calculate. So it's going to be the road width. And then I'm going to add here the building width. And then the spacing twice. And finally, the roundness, I'm just going to use the same one from the road. Now let's return these envelopes for now. These are not buildings just yet, they are just envelopes, but we will use the result of this method and the contents of this buildings array to debug, and we are going to display now those envelopes, even though here I'm already going to write as if they are buildings. Save and refresh. And we see this. It's not really clear, but these are some thicker envelopes than the ones used to define the road. So next step is to avoid these inner segments here. So we do the union of these envelope polys here. And those remaining segments will be guides. I will refer to them as guides here, and they will be computed by doing the union on these temporary envelopes. So I map here just the polys. Let's paste this here and debug. And now you can see these guides appearing here as segments this time. And the buildings are going to be generated on them, but not on all of them. Only if the guide is longer than the minimum length of the building. So let's filter out these very small segments here in the curvy areas and anything that is too short to support the building. We are going to loop through the guides that we have. Let's just take it here like so. And if the length of this segment is less than the minimum length of the building, then we are going to remove that. I will remove the guide at I, one of them, and then we also have to do I minus minus here, because when removing something from an array, it's going to shift everything over this. So then the index at I, where we are, will have some new item that also needs to be checked. So if we let I increase, which it will for the next step, it's going to skip that one unless we decrease as well. Now this segment here, we need the way to calculate its length, and it's really easy. We just go to the primitives segment and implement a length method here that will just return the distance between this P1 and this P2. Now we can save and refresh, and you can see it looks different. These are the only places where buildings can appear in this scenario. The next step will be to generate the supports for those buildings. So, for example, this segment here is quite long, and it's probably gonna support multiple buildings. And I want to get small segments that we can use as a way to define the buildings around them, using envelopes again. You'll see. Now, let's say that we could fit 3 buildings here. I want them to start from here and also have the spacing in between. And the logic for what we're going to implement next is going to be much easier if we consider a little bit of extra spacing at the end as well, because then we can think of a building as the building and its spacing, the building and its spacing, the building and its spacing. And that will help in writing the code. So let's go back to world.js here and define these supports that we need to calculate next, and loop through all the segments of the guides. And for each segment, let's calculate that length with a little bit of extra spacing there. So it's the length of the segment plus this spacing. And now we can find out how many buildings would fit. So the building count is going to be math.floor of the length divided by this building minimum length plus this spacing. And now that we know how many buildings there are, we can find out what is the actual length of the buildings. So the buildings on this segment will have a length equal to the length of this total segment with the extra spacing divided by the building count. But now we have the building and the spacing included in this length. So let's subtract this spacing as well. And we can proceed to generate the supports along this segment with this building length that we calculated. So to do that, I'm first going to focus on the first support. So let's get the direction of this segment. We're going to need it. And then 2 points. Q1 is going to be segment P1, and Q2 is going to be, according to segment Q1, we move along this direction the length of this building length. So what we're going to do is add to Q1, scaling this direction vector by the building length, and add this segment to the supports, like so. Let's implement this direction vector. It's also easy, going to be calculated by normalizing, because I don't want this vector to contain any magnitude, any distance, really. It's going to have a distance of 1, a magnitude of 1, and we just get it by subtracting P1 from P2 like this. So this is going to be the vector from P1 to P2, and it's going to be normalized, so it's just the direction there. This normalization, we don't have it implemented just yet, but it's easy to do. We just go to utils, and maybe here below the scale, we normalize P by just scaling P with the inverse of its length, of its magnitude. And now this magnitude, it's just the distance to the origin. So I'm going to implement it using the hypotenuse there, and I'm only going to pass x and y because the difference is x and y. The other point is the origin. And refresh. I have a typo here. World.js floor. Refresh. And now it works. Looks pretty much same as before, but if we make one segment longer, it doesn't work. I forgot to pass here the supports to the return as well. Okay, now if we make this segment longer, you can see that only the first support for the buildings along this line is shown, and same happens here. So let's do the other ones. We just loop here, starting from the second building until we reach the building count, and update these Q1 and Q2. So Q1 is going to become Q2, but we add the spacing in the direction of the direction vector. And Q2 is going to be Q1 now, but we add in the direction vector the length of the building this time. And we add a new support segment between Q1 and Q2. Let's save this, refresh, and now we can see these supports for the buildings appearing there. Let's generate the base for each of them. Using the envelope with no roundness, we are going to get a rectangular region there, a polygon. So here, after we're done with these supports, I'm going to write bases like this, and looping through all of the supports I'm going to push a new envelope from this segment with the building width as a width, no roundness because it's going to default to just a rectangular shape. And then I take from here the polygon. I don't want to use envelopes here. I just want the polygon. I'm using the envelope constructor to get the polygon that I want, pretty much. And now let's remember to return these bases. And refresh. Yeah. This looks nice, but here there are some intersecting bases, and I'm just going to remove one of them if this happens. So let's go back here and say looping between all pairs of bases to find those that intersect, if some of them intersect. I'm going to loop through all of them except for the last one, and now all following ones. So starting with j at I+1 and going until the base's length to include the final one as well. And now we check to see if basis of I intersects the poly basis of j. And if it does, I'm going to remove, let's say, basis of j because it's the second for loop there, and decrease from the second for loop because of the same issue mentioned previously. Now this intersects poly we need to implement, and we're going to go into Polygon.js somewhere here, maybe, and type intersects poly, a given poly. And we're going to loop through all of these segments and all of the polys segments, and we check to see if there is any intersection between any of these. In theory, it's possible to have a polygon inside another so their edges, their segments don't intersect, but we're not going to have that situation because of the sizes that we have defined and the topology of the network. So let's return true here and return false here. Now let's go back here, and before I refresh, I'm going to save this state so that when I refresh, I'm going to have this same situation. And let's refresh now and see what happens. So this one building from here disappeared. It's okay if we have empty spaces like this sometimes. We're going to fill them with trees, you'll see. Now let's test a little bit. Oh, there is some weird fidgeting happening there on that side. Let me try to isolate when it happens, like this one. There should definitely be a building there. I'm going to save this state and try to fix it. The problem is actually inside of our getIntersection function here. And it's not really a problem of the logic or the math, but it has to do with floating point numbers. Sometimes this bottom here is basically 0, but because of how floating point numbers work, it's not exactly 0. It's very, very close to it. And that's the situation that you see here. The building disappears here because that triggers that bottom to be close to 0 instead of 0, so some kind of fake intersection appears there. And I'm gonna fix this by just using here a small epsilon value. And instead of saying here bottom different than 0, I'm going to say absolute value of the bottom, because it can be either way, is greater than epsilon. And let's refresh and see what happens here. And the problem is gone. And you will see that there is no more fidgeting happening. Now let's move on and generate trees in this region. I'm gonna close some of these tabs I have open here at the top and go back to the constructor here in world.js and prepare a holder for these trees, and they will be generated here. Generate trees in a new private method. Generate trees. And let's start by giving this parameter and say we want to generate 10 trees somewhere in the region occupied by our graph. Now the way this will work is it's gonna prepare a trees array here, and while the length of this array is less than the count, it's gonna try to add more trees here. And for now, they will be just simple points. And I will randomize the location using lerp. So I'm gonna lerp between the left side of the region, the right side of the region, and then from the top to the bottom. And these left, right, top, bottom, we will need to define above. But basically, randomly generating trees within the region is what we're doing here. And let's push the tree into this array and return trees, like so. Now, for this left, right, top, and bottom, top is going to be this point right here. It's the minimum Y value of the buildings and these envelopes. Sometimes the envelope could be the topmost thing, like maybe in this situation right here. And same goes for the bottom. So we need all the points coming from the envelopes forming the road and the polygons forming the buildings. For the road, I'm actually going to use the segments from the road borders that we have already. So here, let's take those points into a variable. Points is equal to, and here I'm going to form an array with from the road borders. Let's map each segment so that P1 and P2 go in a new array. And after all of them are here in an array, so an array of pairs of points, also arrays, we can flatten that into one single array of points. And we do a similar thing also for the buildings, but here we map the points because they are available as part of the poly, and we flatten these as well. Otherwise, we're going to have a big array of small arrays with 4 elements. Okay, and now we get left, right, top, and bottom. So left is going to be the minimum value we map again from these points so that we only take the X value and we spread here. The spread is used just to take individual items, not the whole array. And we've used it everywhere here. And let's do the same thing for the right, but with the maximum here. And let's copy both of these for the top with the Y value here, and the bottom with the Y value here. So min-max is okay here. And let's draw these trees. So similar how we do the buildings here, I'm going to loop and say that through all the trees, draw the tree. They are points for now. Now let's refresh. And you can see something funny happening here. they're generating again and again and again and again at each frame, because here in index.html, we do generate on each frame. And because we use randomness, we get this funny effect going on. But it's kind of okay, because it does show us that the region where they're appearing is indeed what we expect. It's probably time to stop generating this graph again and again on each frame. It's very processor intensive, and only generate it if it changes. For that, we're going to go here and calculate the hash for the graph, a kind of unique identifier. So let's say that the old graph hash is the graph hash. We're going to implement this function soon. And this is going to be the one when the page loads in the beginning. And here, before generate, we are going to check if the graph hash is different than the old graph hash. Then we generate, and old graph hash gets updated to the graph hash, like so. Let's close this and indent these better. And the hash, I'm just going to stringify the graph. So in graph.js here at the top, I'm going to add a hash function that only converts this into a string. Let's refresh. And you can see now the points, these dark points here are now the trees. And every time we change the graph, they actually get regenerated. So what we did works. Next will be avoid generating trees in these illegal places, like on the road here or inside of this building. Let's go to world.js, where we generate the trees. And above this loop, I'm going to have a holder for these illegal polys where we don't want things to be inside. So illegal polys, a new array, and here I'm going to spread the buildings. They are polys still at this stage. Later we're going to actually make a building class for each of them. So we'll have to refactor this code a little bit. But now this works just fine, and from the envelopes, I'm going to take each individual poly like this. So let's check to see if the point that we are adding here should be kept as a tree or not. And I'm going to implement this like so. Keep is true by default, and then looping through the illegal polys. If this poly contains the point P, then we say we don't keep it. Keep is false. And we can also break here, because it's enough that the tree is in one poly. It's not going to be inside another one as well. So no point to look for another one in this case. And here I'm going to wrap this in if keep, then push the tree to the trees. Otherwise, this is going to try again and again until you reach that count. Let's save and refresh. And now the trees don't intersect those. And we could try also changing the graph a little bit just to see multiple generations. And it doesn't seem like any intersection is happening. So the trees are in almost okay places. The problem is these trees also have a size, right? So maybe this is too small of a space for the tree to be in. And that's what we are going to need to do next. Let's define the size for these trees here as another parameter. And I'm going to save it here as an attribute. And when drawing the trees, let's also give them this size so that we see them properly. And I'm gonna give them a color that is transparent black so that we see intersections between trees as well. That's another thing that we're gonna look out for. Close this, save, and refresh. And now you see those things that I was talking about. So these trees, first of all, they intersect, and then also they hit the other objects there. So we need to take care of these somehow. Let's first take care of these trees that intersect. So if a tree is too close to another tree, then we just don't generate it there. We try to generate it again. So back in the generate trees function here, just before we decide if we keep the point or not, I'm going to say if we have kept it so far, we are going to loop through all of the trees. And if the distance from the tree to this point that we want to decide on is less than the size of the tree, then we don't keep it. We can also break. Save and refresh. And now the trees shouldn't intersect each other anymore, because we said that the distance between the trees should be bigger than a tree. So that problem is solved, but let's also solve the problem of being too close to the road or too close to the building polys. So here where we check if the illegal polys contain the point, I'm also going to check or the distance from the poly to the point is less than half the tree size. So here we just need the radius. Let's save and implement this distance to point function inside of the polygon. Maybe here. Distance to point for polygon is going to return the minimum distance between the point and all its segments. So I'm just going to map through all the segments and return the distance to the point from that segment, and then spread and return the minimum of that. Let's save. And now we have to implement the distance from a point to the segment. So we go to the segment file, maybe somewhere here. And I'm going to paste some code. This code is explained in my other video, and I'm not going to go through it now. You can also copy this code from a link in the description. And notice one thing, that the distance to point uses this project point function here. So that's why there are two methods that I pasted here. And also one more vector operation, the dot product, needs to be added in utils. So save this file, and then in utils, where our vector operations are, maybe somewhere here, I'm going to paste this dot product. Now let's save and refresh. And you can see where the trees are now. This is a time when you should be a little bit careful, because, well, if your space is so small that the trees wouldn't be possible to fit, you're going to get an error. And not really an error, but a problem with the execution. Your while here will never end because tree's length will never reach count. So that's why I've used only few trees until now. We would like to write this in a way that it doesn't depend on a count, but on something else. Because if I'm going to make now a very big graph here, like so, it's still going to generate 10 trees. But much of this space is going to be empty. 10 trees in a very, very big city will be nothing. So the way we will rewrite this is not having a counter here, but having a try count here. So what we will do is we will try to add trees. And if at some point we tried a lot, we just assume there are enough trees, we can't add anymore. So what we do here is try count, set it to 0. And here, let's say, while we try for 100 times, we're going to do all of this. If we manage to find the space for a tree, then we reset the try count and then increase the try count on each step. This is very important. Otherwise, we have an infinite loop again. Now refresh the page. And you can see the trees. And they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But the number of trees will really depend on the size of the area here, really. And come to think about it, there are some situations, like, I don't really care what is here in this section. It's so far away from the road. If I think about our self-driving scenario, we will mostly just watch what happens on the road, and we might see some trees here, maybe here if we zoom out a bit, but our focus will be on the road. So generating trees so far away is kind of a waste of memory. And I'm going to add control for that. So let's go here and add another filtering step. If we still keep the tree up till this point, we are going to check if it's close to something. By default, we say that is false, and then loop through all of the illegal polys again. And if the distance from the poly to the point is less than, I'm going to put here tree size times 2. So that I can fit up to 2 trees away from the items. Then I say, yes, there is something nearby. We are close to something. And we can break. We don't need to look further. And here I'm going to say, keep, is this close to something? Now save, refresh. And you can see now the trees no longer get generated in these sections. Now, this piece of code with all this filtering is a little bit long. It's quite long, actually. Maybe should refactor it somehow, extract these as functions. But I'm just going to add here some comments. So this is going to be a check if the tree is inside or nearby the building or the road. And then here, check if trees too close to other trees. And here, avoiding trees in the middle of nowhere. So I think this is fine. Let's save, refresh, and test again. Sometimes these buildings can still be quite close to each other, and I don't like that very much. That spacing is not preserved also here between these ones, because there's this point here on this otherwise straight line. Let me save this state so that I have it for future testing and go where we generate the buildings. Here We check to see if it intersects the poly, but we can also pass now if the basis of I, distance to poly, basis of j is less than this spacing, that's also a problem. And we need this distance to poly function implemented in Polygon.js, but it's going to be quite easy. We just go through all the points and say that for each point we take out the distance to that poly. So now the distance between two polys is actually the distance between the closest points. It's not exactly what we want, because sometimes you might have polys that are offset a little bit, and then the distance will appear to be this, even though they are touching. But it doesn't matter very much in our case because of how aligned the things are. And for this, we would need to have a way to calculate distance between two segments, and I don't have a tutorial for that yet. So it's just going to have to do. Let's save and refresh. And now you can see here that building is gone. It's going to leave an empty space there, but it's just fine. Maybe it's going to get filled by some tree. Like now there will be trees there. Let's test. There's also one more problem here. These buildings are now leaving gaps here again. And this is because of that floating point number issue. Sometimes the buildings that are like this and should have a spacing there don't have it, because when we calculate the distance now, because of the floating point values, just appear a little bit short. So back here in world.js, instead of just spacing, I'm going to add a small epsilon here as well. So minus the epsilon. Save. Let's save this state and refresh. And now you can see that those buildings don't have the gap there.